Charles from GMAT Ninja here. Welcome to episode number 18 in our comprehensive GMAT and Executive Assessment Quant series. Absolutely everything you need for either of those exams in a nice, not too short video series. Today we're going to talk about probability, arguably the most anxiety-inducing topic on the GMAT. Can't say this enough. It's only about 2% of your quant questions on the EA and the GMAT, not something that deserves that level of anxiety. So here's what we're going to cover today. First third of the video is going to be about foundations for the most part, and the questions will be moderately difficult. I'm going to combine multiple things into individual questions, but we're going to cover kind of the word soup, making sure that you're really clear about what to do when you see the phrasing with or without replacement. When you see the phrasing at least one, make sure you're nice and efficient with that sort of thing. As we get into the middle third of the video, we're going to get into questions that are a little bit tougher. So things that require a little bit more intuition, less mechanics. And in particular, the way a lot of people learn probability, especially here in the West, is that you just kind of multiply stuff together and that's what probability is. And it really isn't at all. And we're going to anchor ourselves in this not very exciting definition of probability that a lot of people just don't think about enough. It's the number of desired outcomes over the number of total outcomes. And you'll see what I mean as we kind of get to the middle part of the video, that if you can anchor yourself in that and think intuitively and toggle back and forth a little bit between mechanics and intuition, you'll be really strong, even on fairly tough questions. Now, as we get to the last third of the video today, I'll toss in a gratuitously hard question or two for those of you that just want a challenge. I'm also going to kind of talk about really a family of questions. A lot of the time on the GMAT or the EA, there are questions that use the word probability. They're not really about probability. The probability is kind of the easy part, and really it's about something else, number properties or overlapping sets or combinations and permutations. So I'll give you a little sampling of a couple of those towards the end of the video. And I'm not trying to get through a ton of different topics and cram them all in here. I just want you to be aware that sometimes when you see the word probability, there's nothing really technical going on with the probability itself. Now, who's this video for? Obviously, if you're totally new to studying probability, first third to a half of the video is going to be really valuable for you. More importantly, really who we're aiming this at is people who are just kept up at night about probability, or you walk out of your exam and you go, oh man, the probability, that was the thing that really got me. Again, you probably aren't going to see a lot of it on your exam, but if it's really bugging you, number one, we're going to cover those foundations. Number two, I'm going to be super clear about kind of where that line is between what you really need to know if you're going for a pretty good GMAT or EA score versus what you might want if you're going for a super, super high quant score. Obviously, if you are going for that super high quant score, pretty much everything we're going to do today is going to be at least of some value to you. Maybe the first few will be a little bit easy. Feel free to hit that fast forward button if you're a high flyer and skip ahead to some of the tougher ones towards the end. And again, one of the things we're going to emphasize is if what happens to you when you do probability questions is you find you're just multiplying things blindly. You're just multiplying fractions, not sure why, not sure what it's doing, get a lot of wrong answers or at least inefficient solutions. We're going to address that in quite a few of the questions today. And again, can't emphasize this enough. Only about 2% of your GMAT and EA questions on the quant are going to be probability. So this isn't something that's worth losing a ton of sleep over. Again, if you're going for something like a mid 40s or below score on the GMAT, first half's going to be great for you. Last half of the video going to be more for those of you who are high flyers. All right, with that, we'll warm you up with our first question. All right, as always, if you need a little bit more time, feel free to hit that pause button. All right, nice little warm-up question here with a bunch of different components, just trying to pull apart that word soup you sometimes see in probability questions, but nothing super technical here at all. Got a guy named Harry, 6 different pairs of shoes. 2 of those pairs are pink. and he's going to select 2 individual shoes at random. I'm not trying to be tricky here with the language. GMAT really is never out to be tricky with language. One of the things we kind of tell ourselves, and it just makes our lives harder. They're really, really specific. They're usually phrased super, super carefully. Talking about 6 pairs of shoes. So he has a total of 12 individual shoes in his closet. And 2 pairs are pink, so 4 pink shoes. And we're selecting 2 individual shoes at random without replacement. And we want to know what's the probability, not just that he selects 2 pink shoes, but that he selects a matching pink pair of those shoes. All right. So fairly straightforward in one sense. You're only reaching in. Let's say that all of these shoes are just laying on the ground in the closet. Reaching in twice, picking a shoe first time, and then reaching in and picking another one. So we can kind of set it up as a fairly straightforward little probability problem. On pick 1, we're going to have some probability that he gets what he wants. Pick 2, some probability that he gets what he wants. We can multiply those 2 things together and get our answer. Okay. So on the first pick, what's the probability that Harry ends up happy and gets a pink shoe, or gets something that would set him up to get a matching pink pair of shoes? Obviously, he just needs to get any pink shoe on this first one. He's going to be a happy guy. So 4 pink shoes out of 12. That's the fairly straightforward part here. Call that 1/3 if you prefer. Now, pick 2 is where it gets interesting. So if you're not paying attention, you might say, well, this is also 4 out of 12, or 1/3. Well, why would that be the case? Well, it would be the case if you're putting the shoe back in. That's where this language around with and without replacement really matters. Again, nothing super fancy there, but what we find out of our students is they sometimes just blast right through that kind of language and don't think about whether the shoe's getting replaced or not. Here, it's not getting replaced. So what's Harry doing? He reaches in, grabs a shoe, tosses it behind him. Now what's left in there isn't 12 shoes, 4 of which are pink. What's left in his closet are 3 shoes that are pink and 11 total. So again, nothing technical, just a reminder, make sure you're paying really close attention to that language. And if it isn't obvious from the language, it'll be obvious in some way, right? Even if they don't use that exact phrasing. And it's just a question of making sure you give yourself that extra 20 seconds, take a breath, and make sure that you're thinking through whether this number should be lower on the second pick than on the first. Okay. Now, this still isn't the right answer. Why not? So 4 out of 12 is the probability of getting a pink shoe on that first pick. 3 out of 11 on the second pick getting a pink shoe. But that's not what the question's asking us for. This would give you the probability of getting 2 pink shoes. What we want is a matching pair of pink shoes. So you're not going to wear your pink Uggs with your pink sandals, presumably, which is what you could well get when you set it up this way. And instead, what we want is the match to this first shoe. So 4 out of 12 probability that you get a pink shoe on the first pick. Now there's only 1 shoe in there that's going to be its match. So instead of 3 out of 11, the probability that you get its match is 1 out of 11 shoes that remain. Multiply these together, 1/3 times 1/11th, and we get 1/33rd, and our answer is D. All right, let's give you one more warm-up question. Not necessarily any harder than this last one. Hit the pause button if you need a little bit more time. Okay, nothing more technical here at all. Really just kind of the same foundations we talked about in the first question, just packaged in a slightly different ways, the GMAT and EA like to do. So at a certain barbershop, customers assigned randomly to one of three chairs. We've got a guy who visits barbershop on 3 occasions. We want to know what's the probability he's assigned to a different chair on each visit. So we can just go through each of these 3 visits, nothing super fancy going on, and say, well, what's the probability that he's going to do something on the first visit, that on that first visit he's assigned to a chair that gives him the opportunity to be assigned to a different chair on all 3 visits. So in the first visit, what has to happen? Doesn't matter. He has to be assigned to a chair. Doesn't matter which one he's assigned to as long as the next ones don't match. So your probability that he's going to be set up to have a different chair on all 3 visits, the probability that happens on the first visit that he's set up for that is just 3 out of 3 or 1. What about visit number 2? Now you just have 2 chairs that are left that Bransen hasn't sat in yet, but you're still picking out of those 3 chairs in that random assignment. So your probability is 2 out of 3 on the second visit. And on visit number 3, what has to happen in order for Bransen to get a different chair in each visit? Well, he still has to be assigned to that third chair that he hasn't been assigned to yet. So there's only 1 chair that's going to work out for him if he wants a different chair in each visit. And there's still 3 to choose from. Multiply these guys together. So this is just 1. 2/3 times 1/3 just gives you 2 over 9. And that's it. All right, one more warm-up level question, and then we'll start ramping this up a little bit. As always, if you need a little bit more time, feel free to hit the pause button. Okay, this is kind of the last of our relatively foundational probability questions. After this, they'll start getting a little bit funkier and pretty gratuitously hard towards the end. This one kind of centers on this phrase, at least one. And to whatever extent you see probability questions on the GMAT, again, just 2% of the quant questions, this might be the single most frequently tested concept is, can you look at that and think of the most efficient way to solve it? Now, I see a lot of goofy stuff on this. So this particular question, we've got 4 different customers entering a bar. Each one has a probability of 0.75 or 3/4 if they'll order a beer. We want to know what's the probability that at least one of these customers orders a beer. I sometimes see people just kind of start blindly multiplying here. And again, that's probably the single most common error just in general on probability, is that we think of it as just, hey, I multiply a bunch of fractions together and I get the answer. And it doesn't take a whole lot to make the question just funky enough that that's not going to work for you. So here, kind of mistake I see fairly often is they'll say, well, number one, they might misread this as just 1. So they'll say, well, hey, I need the first one to be a customer that orders a beer, and then the rest will be customers who do not. And this is nowhere close for a whole lot of reasons. Number one is that this is the probability of getting exactly 1 beer, and not just exactly one beer, but the first customer orders a beer and the rest don't. And then we get into this whole bloodbath. You could try to start kind of taking this and going, well, what if it's the second customer and the third? And then you're going to be here for a very, very long time. And there was still obviously that misread embedded in here. So, okay, so that doesn't work. I see that mistake fairly often. Probably equally as common, I'll see students who are encountering this for the first time say, well, what does this mean? So the probability of getting at least 1, so I can calculate the probability of getting exactly 1 customer ordering a beer. So 2 customers order beers. probability that 3 customers order beers, and the probability that 4 customers order beers. And I calculate each of these probabilities individually, and I add all of them up, and I get my answer. And that's pretty brutal too, because number one, these aren't so easy to calculate. We'll talk about that a little bit more later in the video. And also, you've got to calculate 4 different probabilities and then add them up, and it's a ton of work. It's a big mess. So those are sort of the obvious ways that people tend to make mistakes on this. What can you do instead? It's really just recognizing a little bit of logic, and credit to a TA I had way back in undergrad who explained this kind of question this way. He said, well, there's 2 kinds of people in the world. There are households, we'll say 2 kinds of households in the world. Households with no ostriches. And we have households with at least 1 ostrich. And it's like, why is this weirdo talking about ostriches? Well, it was a memorable way. It stuck with me 15, 20 years later of kind of explaining the idea that everything in a situation like this, if you have that phrase, at least one, the complement of it is having none of that thing. So, for example, if we know that 90% of American households have no ostriches, then we know 10% have at least 1 ostrich. Okay, fine. Now we could also express this as probabilities and say you randomly select an American household. What's the probability that you select a household with no ostrich? And instead of 90%, it's 0.9. So then what's the probability that you select a household with at least 1 ostrich? Well, same idea. It's got to be the complement of that. So now you can apply that here and just say, well, what's the probability that at least one of these 4 customers order a beer? It's the complement of no customers ordering a beer. Okay. And that doesn't sound so hard. What's the probability that no customers order beers? Well, probability is 3/4 that they do order a beer. That means 1/4 that they don't. So 1/4 times 1/4 times 1/4 times 1/4. So 4 to the 4th. So 16 times 16, 1/256. That means the probability that at least 1 orders a beer has to be 1 minus 126, or 1 minus 1/256. And that gives us answer choice E, 255/256. And that's all there is to it. Just want to make sure you hit the point where whenever you see that phrasing, at least 1 or something implies it, that jumps off the page. You're also going to see this in probability and combinatorics questions every once in a while. So just make sure that jumps off the page at you and you think through the intuition. What is the opposite, or better phrasing might be, what's the complement of that thing? In this case, at least 1 orders a beer. Complement is nobody orders a beer. That's really easy to calculate, and there's very little math involved in the end. All right. Now we're going to get into slightly tougher questions in this next third of the video. Good luck to you. All right, if you need another minute, feel free to hit that pause button. Okay, now we're getting into questions where it's not just about the mechanics. Now it's about applying some intuition or some sort of logic that's going to get to the question. If you're just kind of using brute force, just multiplying fractions together, this third of the video and the last third of the video, you're going to get yourself into trouble. Here, fairly straightforward sounding data sufficiency question. We got 75 people at a conference. They're all either bartenders or chefs, and we're going to select one at random. And we want to know is the probability of getting a male chef greater than 1/3. One of the things we talk about a ton in quite a few of our videos is on data sufficiency, anything you can do to refresh the question, rewrite it in a way that's logically equivalent, do it every time. That's going to help you a ton, save you a ton of time over the long haul on data sufficiency. So probability of selecting a male chef, is that greater than 1/3? Well, I can rewrite that in terms of the number of male chefs, right? Because I know that there are 75 people there, and I want to know is the probability greater than 1/3. So what I'm really being asked here is the number of male chefs greater than 25 at this conference? All right. And then lo and behold, of course, our answer choices are in terms of actual numbers. We know that there are 40 women at the conference, which means that there must be 35 men. Is it possible for the number of male chefs based on this? Is it possible for the number of male chefs to be greater than 25? Sure. Is it possible for the number of male chefs to be less than 25? Sure, because we have no idea if those 35 men are all chefs or all bartenders or somewhere in between. So statement 1 is not sufficient. And we can cross out AD. Now, what about statement 2? There's 20 chefs at the conference. So if there's 20 chefs, is it possible for the number of male chefs to be greater than 25? Nope. And since this is a yes/no question, this is sufficient. We know for a fact the number of male chefs is not greater than 25, since the number of chefs is less than 25. And therefore, we know that the probability of selecting a male chef can't possibly be greater than 1/3. So statement 2 is sufficient, and our answer is B. All right, let's head to the next one. Good luck to you. All right, if you need a little more time, hit the pause button as always. Okay. So once again, kind of the theme of this video is be really, really careful. If your instinct is always multiply, 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 just take a bunch of fractions, multiply them together. This is the kind of question that isn't super difficult, nothing super technical here, but you can get yourself into trouble if that's your mindset. And really, really basic thing that sounds silly, but we often don't anchor ourselves enough in the definition of probability. Don't think of this as a formula, but what is it? Probability is always the number of desired outcomes, whatever desired might mean in a particular context, over your number of total outcomes. Great. Well, here, let me start by thinking about how many total outcomes do I have? Well, I've got X, Y, and Z, 4 options for X, 3 options for Y, 3 options again for Z. So my total number of outcomes here has to be 4 times 3 times 3, which is going to give me 36. Great. And now the question is, how many desired outcomes do I have? These questions are typically rigged so that there's not going to be a ton of different ways to calculate it. Notice that if we take the biggest numbers from each set, so the 5, the 7, the 9, we're going to get 21, which isn't so far from 19. Also notice that we're being asked for the probability that x plus y is greater than 19. So what is our desired outcome here? Our desired outcome is just that the sum equals 20 or 21. That's not so bad. Now, how many ways are there to get a 21? Well, that's just one way. I've got to have 5, 7, 9. And now how many ways to get 20? There can't be that many of them. These are nice consecutive integers in each of these sets. So all I can really do is take the biggest number in each set and turn one of them into a slightly smaller number. That's the only way I'm going to get 20. So I could have 4, 7, 9. Or I could have 5, 6, 9. 5, 7, 8. And that's it. There's very clearly no other ways to do it the way these numbers are set up. And again, very, very typical sort of thing you might see on the executive assessment or the GMAT. A little bit intimidating. If you try to be too formulaic about it, get yourself into trouble. Looks like it's going to be a lot of work, but in the end, it's not a lot of work because the numbers are arranged in a way that there just aren't that many options. There aren't that many desired outcomes. I've only got 4 of them, and that's the end of the story. So my probability here is those 4 desired outcomes over those 36 total outcomes. That's going to reduce to 1/9. And my answer is C. All right, one more kind of mid-level, sort of funky, sort of conventional, all at the same time, probability question, and then we'll ramp it up in the last third of the video. All right, if you need a little bit more time, hit the pause button. So leading to this question, I called it sort of conventional, sort of funky all at the same time. But why do I say that? I call it sort of funky because this is a relatively rare thing on the GMAT. How often are you going to see a question that asks you for exactly 3 of the 4 things, or exactly 1 of the 4 things, or exactly 2? Very, very rare variant. Maybe there are 3 or 4 official questions in print out of the literally thousands that have been published that get at this exact concept. So in that sense, not going to see it a whole lot. Is it conventional in another sense? Sure, because the kind of logic you need in order to solve it is something that you should be able to master pretty easily without knowing anything terribly technical. Now, that said, a whole bunch of different ways to solve this question. So you could solve this using binomial expansion. If you don't know what that is, do not worry about it at all. It is not something that is necessary by any means on the GMAT. Some people with really strong technical backgrounds in math like to solve it that way. Good for them. That's fantastic. You could solve this using combinations. Again, if that's something that you're really comfortable with, good for you. I'm not going to talk about that here. We have a separate video on combinations. And I think it's just easy to solve this with a little bit of logic and basic probability. So that's our third path. That's what I'm going to show here. So I could kind of start by saying, well, okay, exactly 3 will order pie. So just to write down the exact numbers here. So probability of ordering pie is 3/4. Probability that you do not order a pie is 1/4. And I could kind of go through and say, well, let me kind of do our good old thing of kind of these 4 different selections, 4 different customers walk in. And there's a whole bunch of different ways that you could get at this because it doesn't matter which of these customers does and does not order the pie, as long as you have 3 that do and 1 that doesn't. So how many ways are there to set that up? Well, you could have the first one order pie, and the second one orders pie, and the third one orders pie. No pie for that last guy. Same idea, except it's the third one that doesn't get the pie, and so on. I'm not saying you need to draw all this out. What is really useful is to recognize the concept here that you have the probability that, let's say we calculate the probability that the last one doesn't order pie, but the first 3 do, and we get 3/4 times 3/4 times 3/4 times 1/4. Great. My point is that you're going to have that exact same probability 3 more times. Oops. So first one doesn't order pie, second one, third one, and fourth one do. So there's 4 ways to rearrange this. So if you can recognize that the probability that the first 3 do order pie and the fourth one does not is this number, and then it's going to be exactly the same if it's the third one that doesn't get pie, or the second one that doesn't get pie, or the first one doesn't get pie. As long as you can recognize that logic, you can solve any question that looks even vaguely like this, because all you have to do is recognize that intuition and say, well, I'm going to take this original probability, multiply it by 4, and I'm done. So here we get, I'll rewrite all this. So 3/4 times 3/4 times 3/4 times 1/4 is the probability that the first 3 order pie, last one does not. But that's going to be exactly the same as these. Multiply this by 4. We can cancel out these 4s, and we just get 27/64. And our answer is C. So a lot of what happens on the GMAT, especially get into some of these more, I don't know, exotic question types, a lot of the time it's basic foundations. They start building a little bit of logic on top of that. And it's not that you need to know anything more technical. Again, you could, binomial expansion, a whole bunch of combinatorics. You could do that. That's wonderful. If it works for you, fantastic. If not, if that's not your cup of tea, no worries. Just apply really strong reasoning, and you're going to be in really, really good shape. All right, we're 2/3 of the way through the video. This last third. So this next question I think is the toughest in the video. It's within the boundaries of the GMAT. It's based on a few things we've seen before. Super, super tough, about as hard as probability gets. From there, we're going to cover 2 questions that are not really about probability at all. They use the word probability, built on a very, very super basic foundations of probability, but it's really kind of combining other things. I want to illustrate a couple of those at the end. So again, if your score goals are modest, you don't really need to watch this last third of the video, but if you're having a good time, stick with us, and this one will give you a good challenge. All right. If you need a little more time, feel free to hit the pause button as always. Look, this is about as hard as probability questions get on the GMAT. If I were to go through the several thousand official questions that have been published or things we've seen on the actual exam, I don't think we're going to find 5 questions that are tougher than this one. Now, this is derived from official questions. There are some that get at the same kinds of concepts in similar ways, but there are very, very few of these, very few that are harder. So if you found this easy, good for you. You're doing phenomenally well. If you struggled a little bit on it, you're probably still doing pretty well. If it was just minor struggles, if you got obliterated by this, no shame in that at all. This is not something you absolutely need to get, especially if your goals are something like a 47 or a 48 or anywhere below that on the GMAT quant. This isn't something you need to lose too much sleep over. Now, that said, the thought processes definitely are things that are fair game. It's kind of a matter of toggling back and forth between a little bit of algebra and a little bit of intuition. So I'm going to try to model that here. All right, we got 9 dogs at the animal shelter. We're going to choose 2 at random. We want to know the probability that we get at least, well, we want to know whether the probability of getting 2 Labradors is less than a half. Now, as always on data sufficiency, the more I can do to rephrase that question in logically equivalent ways, the better off I'm going to be. So let's try that here and see where I can take it. So that question, probability of getting 2 Labradors, if we let L equal the number of Labradors, let's see where that algebra is going to take us. So on that first pick, probability of getting a Labrador is L over 9. Second pick, well, there's going to be 1 fewer Labrador available, 1 fewer dog overall. So there's my probability of getting 2 Labradors. And I want to know, is that less than a half? Now, next thing I want to do here, I can rearrange a little bit. So my first instinct, 9 times 8 is 72. So what if I multiply both sides of the inequality by 72? What's going to happen there? So then I get L times L minus 1 less than 36. And you've seen this modeled in other videos. If you've been with us on these, Bransen in particular, in some of his videos that went pretty heavy after algebra and data sufficiency, I always kind of leave that question in there just so that I'm clear about what's a fact given to me and what's the question being asked. So my question here is the number of Labradors times 1 minus that less than 36, logically equivalent to this. So what does that tell me? Or how am I to rephrase that again? Well, when is this going to be the case? So my first instinct is, okay, if there's 6 Labradors, is this going to be a true statement? So if L is equal to 6, then my answer to this is yes. 6 times 5 is indeed less than 36. And now what if I go one bigger than that? 7 times 6, is that less than 36? No. And the answer to my question is no. So think through that a little bit. My probability is always going to be less than a half if I have 6 Labradors or fewer. If I have 7, 8, or 9 Labradors, then it must be true that that probability of getting 2 of them will be greater than a half. So now I can rewrite this question. So is the number of Labradors, less than or equal to 6? Logically absolutely equivalent to this guy. Okay, great. Let's tackle statement number 2 here. So the probability that we get 1 lab and 1 non-lab is greater than a half. This is where it gets really fun. So L over 9, let's say we get a Labrador on the first pick, times a non-Labrador, I'm going to call that N here, over 8. And that's going to be greater than a half, but you got to be careful here. The way I just wrote this up, that's the probability of getting a Labrador on the first, non-Labrador on the second. And that's not quite what I'm going after. I don't care about the order here. I want to know the probability of getting exactly 1 lab, exactly 1 non-lab in any order. So what that's going to be, what I just calculated here, is the probability of getting a lab on the first one, non-lab on the second. That's going to be equal to the probability of getting a non-lab first and then a lab. So if I want the probability of getting exactly 1 of each, I've got to multiply this thing by 2. And I'm going to do the same kind of thing I did up here. So I'm going to cancel this out, cancel the 2 with the 8, I get a 4. Now I'm just going to multiply both sides by 36. 9 times 4 is 36, just so that I get this simplified nicely. So this is going to give me the number of labs times the number of non-labs. 36 divided by 2 is going to be greater than 18. And now I just have to think through, what kind of values does this give me? So if I have 1 lab Let's start with the big number here, I suppose. What if I have 9 labs and no labs? Then obviously this is not going to be true. So that can't be the case. Well, what if this is an 8 and a 1? Still can't be true, right? There's no way I can have 8 labradors here because the number of labs times the number of non-labs is not greater than 18. What about 7 and 2? Still not working for me. But now we're getting close, right? Could I have 6 labs? Not quite. Still not quite. But what about 5 and 4? Yep, that's going to be greater than 18. I could have 4 labs and 5 non-labs. That's going to be greater than 18. And then we start repeating numbers, right? So could I have 3 labs? Nope, that's not greater than 18. So what is this saying? This is saying I either have 4 or 5 labs. It takes a little bit of trial and error to get there, but notice again, the numbers aren't that big. So what this tells me is that the number of labs is either 4 or 5. Now let's come back to our question. The question is, do I have 6 or fewer labs? Absolutely, because I have either 4 or 5 labs based on statement 1. Thanks to that, statement 1 is sufficient. We can cross out B, C, E. You having fun yet? All right, I'm going to erase some of this in the interest of space. Probability I get 2 non-labs in statement 2 is greater than 1/10. So I can say again, n over 9 times n minus 1. So n is the number of non-labs. First pick, the odds of getting a non-lab are n over 9. Second pick, 1 dog is gone, n minus 1 divided by 8. This is greater than 1/10. Same sort of deal we did before. I'm going to multiply both sides by 72 by 8 times 9. And that's going to give me this guy. N times n minus 1 is greater than 7.2. And again, we're back to that beautiful land of strategically picking numbers here, not blindly, but just trying to think through, can I get to sort of a range of values for n? Well, is it possible to have, I'll start with small numbers and work my way up since this is awfully small. So is it possible to have 2 non-labs? Nope. 3 non-labs, 3 times 2, not greater than 6. But what about 4 non-labs? 4 times 3 is indeed greater than 7.2. And then as I make n bigger, I'm in business, right? So what is this saying to me? It's saying that n is at least 4. So if there's at least 4 non-labs here, that means that there's no more than 5. So the most I could possibly have. So if the least number of non-labs I can have is 4, the greatest number of labs I can have is 5. So I've got 5 or fewer labs, and that's perfect. Exactly what we're looking for. I want to know, is the number of labs equal to or less than 6? And statement 2 is telling me the most I could possibly have is 5. So that's sufficient as well. And our answer is D. If your head is spinning, don't lose any sleep over it at all. The odds that you see something quite this complicated are virtually zero. But again, notice all this is a little bit of algebra, a little bit of really fundamental probability. And then we're just kind of going through and just thinking through the numbers as logically as we can, keeping our information straight, a little bit of trial and error and just thinking intuitively about the numbers. And that's all there is to it. It's just that there's so much of it that the question gets pretty bogged down. All right. Last 2 questions here. We're going to mill it out a little bit. These last 2 are questions that use the language, use the term probability, but really the heart of the question is about something else. I want to illustrate a couple of examples of those, and then we'll wrap this up. And if you need another minute, feel free to hit that pause button as always. Okay, now we're in the not really probability section of the probability video, on these last two questions. So not infrequently in questions that seem to be about probability, uses the word probability. Sure, it's based on that basic foundation that your probability is the number of desired outcomes over the number of total outcomes. But fundamentally, what makes the question difficult really isn't the probability at all. It's something else. In this case, this is really a number properties question disguised as probability. If you struggle a bit with number properties, please check out Harry's 2 videos earlier in the series. Absolutely fantastic, pretty comprehensive treatment of number properties. Here, I'm going to assume that you have some basis in it, because that's really the heart of what we're going after here. And for what it's worth, if you're not interested in number properties right now, no problem. Skip ahead to the next question. All right, integer n is chosen randomly from the numbers 21 to 100 inclusive, and I want to know the probability that n times n minus 1 times n minus 2, so 3 consecutive integers here, multiplied together. I want to know the probability that that product is going to be divisible by 8. First thought here is, well, how many integers do I have total? What's my denominator going to be? What are the total outcomes, total different options for n? Well, this works out nicely. This is going to be 80 integers. And that makes sense, where we want to know something about what fraction of those are going to be divisible by 8. Kind of nice that the number of total integers is divisible by 8. Good. Okay, now it's just about figuring out what are the different scenarios that might give me a multiple of 8 here. So my first thought is, let me think about even numbers and see if that gets me anywhere. So let's say that we have that n is even, which would make n minus 1 odd, which would make n minus 2 even again. And the first instinct is, well, that doesn't tell me anything, because you could have 2 even numbers. Maybe they're multiples of 8, maybe they're not. Yeah, but think about what's going on with the product here. So to be divisible by 8, what we need is one of these numbers to be divisible by 4, the other by 2. Put another way, somewhere in this string of numbers, we need 3 2s in that prime factorization. Whichever way of thinking about that works best for you. Now think about what goes on here. If n is even, n minus 2 is also even. Now, at least, well, exactly one of those needs to also be a multiple of 4. Why is that? If it helps, spot the pattern here. So just taking a random sample of consecutive even integers, not a multiple of 4, obviously a multiple of 4, not a multiple of 4, multiple of 4, not a multiple of 4, 12 is a multiple of 4, and it's going to continue like that into infinity. So, okay, well, let's say that this first one is not a multiple of 4, but it's even. That's going to have at least 1, 2 in its prime factorization. Then this one would have to be a multiple of 4. Multiple of 2 times multiple of 4, we're getting a multiple of 8. Doesn't matter whether this one's a multiple of 4 or not. If it is a multiple of 4, great. That's just a multiple of 2. We still get something divisible by 8. If this is not a multiple of 4, then this one would be. Either way, as long as n is even, I know that this product of these 3 consecutive integers is going to give me a number that's divisible by 8. So what's the probability that this is the case? Well, 50-50 shot, right? Out of any 80 consecutive integers, 40 of them are going to be even. So I know that my probability of getting an even here on that first, that n is even, the probability that n is even is going to be 1/2. Okay, let's hang on to that. And now think through, are there any other scenarios? Is there any other way for me to get these 3 consecutive integers multiplied together to be a multiple of 8? Well, what if this middle number is a multiple of 8? What if n minus 1 is a multiple of 8? That's the only other way to do it, right? So n times n minus 1 times n minus 2. We've already accounted for all the possibilities that we start on an even. So this is odd. This is even in this scenario. And this is odd. And I want to know, what's the probability that this is a multiple of 8? And that's easy enough, right? So out of any 80 possible values for n minus 1, exactly 1/8 are going to be multiples of 8. So I'm going to get 10 of those out of those 80. So the probability that I get a multiple of 8 here in this middle term is going to be equal to 1/8. Great. Any other scenarios? Nope, I think we've covered it. So if the middle number is even, so if n is odd, n minus 1 is going to be even. Probability that this is a multiple of 8, total 1 out of 8 different values of n are going to give me a multiple of 8 here. And then 1 out of every 2 occasions, I'm going to get an even number on the first, which gives me a multiple of 8 as well. 1/2 plus that 1/8 just gives me 5/8. And my answer is D. And just to be clear, pretty darn tough question here. Even if you're pretty good at number properties, even if you're great at probability, you might struggle a little bit with the number properties and logic here. No shame in that whatsoever. One last question, actually not super hard to end the video, but I just want to kind of illustrate how a lot of these questions end up being kind of interdisciplinary. It's a probability question in terms of the language, but really it's about combinations and permutations. Give you guys a couple minutes on this one. All right, if you need a couple more minutes, hit the pause button as always. All right, last question of the video. My point here isn't that you need to know a ton about combinations and permutations. It's not where we're going with it, but it really is that probability doesn't involve that many different technical wrinkles. So what have we covered in this video? We talked about basic language with and without replacement, talked about at least one, and being able to think about that a little bit inside out. Really, really useful shortcut. From there, it's really just a question of anchoring yourself in the basics. Probability is always the number of desired outcomes over the number of total outcomes. If you can hold on to that intuition and not blindly multiply, you can answer a whole lot of really tough probability questions well, and you're also very unlikely to see a ton of them. There really isn't anything lurking over there. There's no probability boogeyman where there's some magic formulas you need to learn. As long as you can anchor yourself in a little bit of basic logic, follow some intuition on these questions, there's really not a lot that you need to memorize, not a lot of variance on any formulas, nothing like that. It's really a fairly simple topic, induces a ton of anxiety. And maybe part of it is that a lot of probability questions, again, aren't really probability at all. So it uses the word probability, you bet. So we're going to have to calculate the number of desired outcomes and the number of total outcomes and divide one by the other. But really, this is about combinations and permutations, combinations in this case. So if you have not seen this before, we have another full video on combinations and permutations coming up next. But here's your basic formula for it. If you don't know that, I'm going to keep steaming ahead as if you do. You can watch that other video if you need to go back through the basics with us. So here, what's going on? I got 6 chocolate chip cookies, 4 oatmeal raisin cookies. I'm going to select 4 at random. I want to know the probability that I get 2 of each type. So I'm going to start here. What exactly is it that we desire? What's the desired outcome? So 2 chocolate chip cookies and 2 oatmeal raisin cookies. And what's the total outcomes? That's ways to get 4 cookies from 10, right? So if I randomly select 10 cookies, how many ways can I get 4 of them? And now how many ways can I get 2 chocolate chip and 2 oatmeal cookies? Okay, really, this is just recycling this formula 3 times, and that's all there is to it. So I'm going to start with the ways to get 4 from 10. So 10 cookies, I'm going to choose 4, punch it into our handy little formula here. 10 factorial over 6 factorial, 4 factorial. So 10 times 9 times 8 times 7, 4 times 3 times 2. The 8 cancels, the 3 cancels, and I get 210. There's my denominator up there. How How many ways can I get 2 chocolate chip cookies? That's just going to be 6 factorial over 4 factorial, 2 factorial. So 6 times 5 over 2, that's 15. And I'm running out of space. My oatmeal raisin cookies, I've got 4 to choose from. I'm going to choose exactly 2. Punch in the formula once again. 4 factorial over 2 factorial, 2 factorial. That should give me 4 times 3 over 2, or 6. Okay, all I've got to do is punch these in and I'm in business. So I'm going to erase this guy now. So how many desired outcomes? I've got 6 ways to get 2 oatmeal cookies, 15 ways to get 2 chocolate chip cookies. Multiply those 2 together. So I get 90 total combinations of 2 different chocolate chip and 2 different oatmeal raisin cookies. How many total ways can I select 4 from that group of 10? That's just the 210 here. And I can simplify a little bit. I get 9 over 21 by dividing top and bottom by 10. Divide top and bottom by 3. And I get 3/7. And D is my answer, and that's all there is to it. All right. Biggest takeaway of this video, please don't let probability keep you up at night. Number 1, can't say this enough, not the most important question type, not even close. 1 out of every 50 questions, maybe, on your GMAT or EA quant section is going to be probability. From that perspective, don't lose too much sleep over it. And also, even if you are shooting for a super, super, super high score, or you just want to master it because it keeps you up at night, it does bug you, there's not a lot to master here. Basic set of intuition, basic definition of probability, couple of fundamental little pieces of technicalities, language to watch out for. That's really all there is to it. There's nothing else lurking there. You don't want to sit up and study probability for hours on end. There are far more important things on the test. When you do encounter it, just anchor yourself in the basic intuition, even if the question's pretty funky, and you're going to be in perfectly good shape. All right, that wraps this one up. Thank you so much for watching, and we'll see you next time.